So welcome back. So we were discussing about powder compaction processes in case of pressure assisted compaction. So we will continue with that, and in this class we will also discuss about the atomization techniques, how we can achieve desired powder particle shape and characteristics. So we will go into the details of it. Continuing with the uniaxial compression compaction. So it is known that the presence of frictional forces limits the degree of densification. So usage of lubricants either mixed or applied to contact surfaces can be done to minimize friction. So this process is pretty same like we have discussed earlier. So here you can see that lower punch is basically initially stationary, where the powder aggregate is loaded within the die cavity, then the upper punch is pressing it, and then once the required green density is achieved, then the upper punch moves back, and then the lower punch also moves up, and then it ejects the component, and then the feed shoe is because of its lateral movement, it takes the component green compact out of the die punch assembly. So this is a typical configuration of upper punch, lower punch and the die cavity, and this is the PM spar gear. So this is a typical example of uniaxial compression technique, obtained green compact of spar gear, and then this is the core rod, because this is a hollow spar gear we are talking about. So this is the hollow shape is achieved by the core rod. So these are some of the typical shapes which can be manufactured by uniaxial compression technique. However, when there are more complicated shapes are in consideration, then this uniaxial compaction technique may not be capable of producing those shapes with required level of structural integrity and microstructure and property attributes in the sintered part. So then we need to go for advanced powder metallurgy techniques, for example injection molding, that we will be discussing later in this module. So so here mostly we use mixed lubricant, not a single lubricant we use. So it reduces interparticle friction and aids in better packing. They also affect the densification property depending on their volume and density. So the mixed lubricants would be removed before sintering. So this is the stage that is called debinding. So the debinding can be achieved by two means. Number one by solvent debinding. So that can be achieved by appropriate solvent which are capable of dissolving the polymers, and even in case of organic polymer based additives or lubricants, we can even use water as a for thermal solvent debinding. So polyethylene glycol (PEG) is a particular organic polymer that can be removed by immersing the green compact in water. So this is a typical example of water based solvent debinding. And post solvent debinding, it is thermal debinding. So where the residual binders present within the green compact are completely removed, and then basically after thermal debinding we are talking about a porous object where the powder particles in the vicinity are present. However, there are big pores which are present, which are basically created due to the removal of the complete polymer network, which are then get densified, and then the shrinkage happens in the final sintering stage, and where we can achieve the density as high as 97 to 99% based on the particular powder metallurgy technique we are discussing about. So the die wall lubrication can be achieved by graphite and molybdenum disulfide, which can be applied physically on the die punch assembly and the surfaces, and they can be easily removed, but takes longer production times. Commonly used lubricants for powder metallurgy are paraffin wax, aluminum stearate, lithium stearate, etc. So based on the part geometry and part dimensional attributes at different sections of the part, we can classify the PM powder metallurgy parts in 4 classes. So, that is class 1, class 2, class 3, class 4. So, class 1 deals with the simple thin sections. Unidirectional pressing is enough to develop class 1 parts, and then class 2 part, they are simple, but having thick sections requiring pressing from 2 directions. So, that means so then if I consider a die punch assembly, then in case of I mean class 1, there is only one punch needed, which is movable, that is unidirectionally pressed, and then class 2 we need 2 direction. So, this is in case of class 1, and both of them in case of class 2, and then in case of class 3, 2 different thickness level requiring 2 direction pressing. So, typical example of this can be like this. So, this is a case where we need one punch at the top and 2 punches at the bottom. So, then this is a typical case of class 3. Okay. And then there is a case of class 4, then multiple levels of thicknesses requiring pressing from both the directions. That means, with even further steps involved in the thicknesses, a typical example can be like this, like a stepped part where multiple punches can be needed, and this thickness cross sectional variations can be at one side, can also be present in the other side like this. Okay. Yeah. So, this is a typical part, representative part, which is a demands which is classified as class 4 PM part and needs appropriate die punch arrangement if it is intended to be manufactured by unidirectional if it is intended to be manufactured by uniaxial pressing technique. However, there are other advanced techniques, for example, injection molding, isostatic pressing. They are generally employed for parts having a higher degree of complicacies, and also where higher degree of precision is needed. So, tooling, a single action tooling, pressure is applied by lower punch while the die cavity and upper punch remain stationary. So, after compaction, the upper punch moves away and compact is ejected by movement of lower punch. So, class 1 parts can be made by this tooling as shown to you earlier in schematically, and double action tooling for all 3 class 2, class 3 and class 4 type parts are made by this tooling when both the punches are simultaneously moving in the opposite direction, so that they can pressurize the green compact. Pressurize the powder aggregate to develop the green compact with the desired level of green density. So, powder characteristics that affect the tooling design includes flow of powder. So, powder particles should flow freely. To fill the die by using lubricants, flow can be made smooth and improved. And then die fill, this is the amount of powder in the cavity before compaction. So, this depends on shape and geometry of the part, free flow of powders, complexity of the part like thin sections and protrusions. So, die material. So, die material based on the the kind of pressure to be exerted over the die materials can be made of it can be made of aluminum. It can also be if we are dealing with soft powders. So, we can also mostly use like hardened steels, die steels. We can also use tool steels for relatively hard powders, and harder and abrasive powders like steel tungsten carbide dies are also used. But carbide dies are costly and having high hardness and also difficult to machine, and sometimes they are brittle also, and their handling becomes extremely difficult because you need to be very much careful. One need to be careful. Sudden impact or drop impact due to drop can cause their breakage or breakage of the functional parts or the intricate geometry. So, hence it is advisable to use die steel, tool steels, which also along with the required level of strength, abrasion and resistance, it also offers some level of ductility as well. So, which increases the longevity of the dies to a greater extent. So, the coated dies with hard and wear resistant coating material like titanium nitride or titanium carbide can also be used. So, then in that case the coating, that is titanium nitride or titanium carbide, can facilitate the need of the wear resistance that is needed to handle very hard and abrasive particles, such as when we are dealing with the processing of the ceramic powders. So, that can be accomplished. So, defects occurring during die pressing of powders are lamination cracking. So, this is caused by trapped air in compact sample. So, this cracking occurs perpendicular to the loading direction. So, again assume that this is a cylindrical compact and we are basically doing uniaxial pressing from both the directions. So, in that case you can understand that so this is because this is the application of load. So, if there is a cracking perpendicular to the loading direction, so we can call it as lamination cracking, which happens due to the entrapment of the air in the form of bubbles in the compact powder aggregate, which are getting transformed in the form of green compact. So, this cracking occurs perpendicular. So, blowout, this is another kind of defect which occurs when all the entrapped air tries to escape at the interface between the die and the punch. So, what is the interface between the die and the punch? So, as we have learnt earlier, so this is a typical die and punch system where punch moves through the annular space within the die cavity, and then when it is, so it is basically the blowout happens at the interface of die and punch. That means so where this is the happens in the annular space of the die cavity where the mating punch travels through that. So, so it is basically a defect that is generally observed in the surface of the PM part that is being manufactured, or that is being compacted in the die punch assembly, and because the entrapped air is getting exiting at the interface. So, that means the interface of punch and die is basically the surface of the green compact which is getting developed. So, likewise, and then when we are talking about even improved properties, then we can achieve in case of uniaxial compaction of powder aggregates. So, then this is a typical example of the isostatic compaction is cold isostatic compaction. So, it is a compaction process in which isostatic fluid pressure is applied to a powder mass at room temperature to compact it into a desired shape. So, the powder parts can be compacted up to 80 to 90% of their theoretical densities. Water or oil can be used as pressurizing medium. So, what is the process details? So, here high density or near net shaped green parts, long thin walled cylinders, parts with undercuts can be readily fabricated. So, in this process pressure is applied simultaneously equally in all directions based on the Pascal's law that you must have studied, because of which the pressure within the fluid medium at all the points is same. So, using a fluid to an elastomeric fluid with powder at room temperature. So, sintered CIP component can reach up to 97% of the theoretical density, which is much higher than the density we can achieve by loose powder sintering or even by uniaxial compaction assisted sintering. So, there we can the density varies between 87 or to 95%, whereas we can go up to 97% of theoretical density of the material concerned by employing cold isostatic pressing technique. So, steps involved in the process are select elemental or pre-alloyed powders, then fill the mold with powders, and then load mold into the press, that cold isostatic pressing press, and pressurize the mold containing powder aggregate, and then hold the pressure for a while and then depressurize and remove the mold, and removing the compact sample, and then post subsequent sintering of the sample to achieve the desired densified part. So, based on the technique followed, cold isostatic pressing can be classified as two different techniques, that is number one is wet bag process. So, in this case the mold is directly in contact with the fluid media, that is responsible for exerting pressure over the powder aggregate to facilitate its compaction, And another important thing that you can achieve, because it even you can understand from the name itself, like the major concern we have seen in case of uniaxial compaction, that the density gradient. So, that can be completely nullified, nullified to a greater extent in case of cold isostatic pressing. So, barring some complicated cross sectional regions, it can cold isostatic pressing can facilitate uniform density distribution within the powder compact. So, this reduces the productivity, since however, in case of wet bag process, wet bag technique of the cold isostatic pressing, we can see reduced productivity, since the bag vessel have to be removed every time before refilling. So, tooling costs can be, of course, the tooling costs are reduced in this case, whereas in case of fixed mold process, where the mold can be reused again and again, and we need not to remove the mold every time, rather we can eject out the part of the mold. So, in this case the mold is fixed in the pressure but powders are filled in situ. The tooling has internal channel into which the fluid is pumped within the internal channels, and thereby the fluid is pressurizing the powder aggregate which is kept within the mold. So, this is an automated technique in which the powder filling, compaction of the powder aggregate, and then ejection of the depressurization and removal of the green parts are done continuously. So, this involves higher tooling cost, but has higher production rate as well compared to wet bag based cold isostatic pressing technique. So, advantages of CIP are, it is uniform, controlled, reproducible densification of powder, longer slender parts can be processed, near net shape forming, short production times, economy of operation for complex and large parts. Applications of CIP, some examples of applications taken from industrial processes in present days can be listed below. So, the applications of CIP is graphite, cold isostatic pressing of electrographite, refractory graphite, and graphite used in nuclear reactors, and then ceramics. So, cold isostatic pressing of tubes, nozzles, tiles and linings made of special ceramics, then ferrites, that is parts used for permanent magnets, computer memories, electronics, etc., and then cemented carbides and also metal powder. So, high speed tool steel, super alloys, stainless steel, titanium alloys, beryllium. So, in this case the application again try to understand, here we are not talking about net shape parts, rather we are talking about developing special purpose alloy specimens, and which are otherwise difficult to alloy develop by other means, other routes, like for example by melting casting routes. So, they can be effectively manufactured by PM route, for example cold isostatic pressing, where we are basically talking about developing the preform or sample, and then we can do the post finishing operations such as machining and heat treatment, etc., to achieve the desired set of properties in the sintered part. So, the other pressure assisted compaction techniques, examples are rolling, powder rolling. So, this process involves feeding of powder. So, this is a typical example of a too high rolling arrangement. So, too high rolling, this is what you can see over here. This is responsible for generation of a green strip. So, until now we were talking about the green compact that is developed from the powder aggregate. Here we are talking about developing a green strip with the help of a too high rolling arrangement. So, this process involves feeding of powders between rolls to produce a coherent and brittle green strip. So, this green strip is then sintered and re-rolled to obtain a dense and finished product. So, the steps are firstly to preparation of the green strip, then sintering, then densification of sintered strip, and then final cold rolling and annealing of the sintered strip. Okay. So, the parameters affecting powder rolling are roll diameter, roll gap, roll speed, and also powder characteristics. Okay. So, how they are affecting the quality of the green strip and thereby the sintered strip that can be manufactured by this powder rolling technique. So, so large roll gap leads to the decrease in grain density of, so which is understandable, because as we are increasing the thickness. So, large roll gap signifies that we are we are basically trying to achieve higher thickness of the green strip, and in that case it becomes difficult to maintain higher green density. So, hence small roll, however, if we are talking about very small roll gap, then we can often see the case of edge cracking that is intrinsic with the rolling process, which are not designed effectively. So, this is happens in the green strip when we are talking about very small roll gap. So, of course, so there is an optimum roll gap, again where the role of this numerical modeling comes in a big way. So, we will be discussing the process modeling section of this module also subsequent classes. So, so this is the optimum powder roll gap that is necessary, and then roll diameter. As the roll diameter increases, there is increase in density can be achieved, and also the strength also simultaneously can be increased with the roll die because of higher surface area of the pressurizing media. In this case the rolls, we can achieve higher densification at the green state, and that is why the enhanced density and strength can be achieved in the green strip. And roll speed kept low, 0.3 to 0.5 meter per second, higher because we are talking about preparation of the green strip first. So, higher roll speed can cause disintegration of the powder particles before allowing them to develop cold welding with each other, so that they can maintain the shape and desired dimensional attributes in the sheet. So, that is why speed has to be checked. And then powder. So, irregular powder with rough surfaces provide better interlocking, and that is why they can facilitate achieving higher green density or higher strip green strip density. Of course, there is problem there are problems in the sintering state that we have discussed earlier. Hence, we always recommend to go for powder particles having higher sphericity as much as possible. So, applications are nickel strips for coinage, nickel iron strips for controlled expansion properties, copper nickel tin alloys for electronic applications, and porous nickel strip for alkaline batteries and fuel cell applications. So, these are the typical applications for the powder rolling process. So, now we are now talking about special powder metallurgy techniques. So, we have already discussed about cold isostatic pressing, and now we will discuss about the hot isostatic pressing. So, which is quite similar with cold isostatic pressing. The difference lies in the processing temperature. So, here we are talking about simultaneous exertion of the pressure as well as temperature on the powder aggregate. So, here we are talking about simultaneous sintering densification and also pressurization. So, which can yield significantly improved properties in the sintered parts, which that means which can be much higher than the conventional uniaxial compacted and then sintered parts. That means, it can yield properties better than the classical PM route of initial compact preparation via pressurization and subsequent thermally activated sintering process. So, because here both the processing stages are coupled, so we can achieve properties which can even compete or even overperform compared to the cast or forged form of the same material, because of the better microstructural control that we can achieve in case of this PM route. So, so it is an ideal method for consolidation of powders of nickel and cobalt based superalloys, tooled steels, merging steels, titanium alloys, refractory metal powders, cermets, etc. So, it has got variety of applications including bonding of dissimilar materials, consolidation of plasma coatings, processing hard and soft magnetic materials, etc. So, so this is a HIP is the application of pressure at elevated temperatures to obtain net or near net shape parts from metal, ceramic, cermet powders. And HIP unit consists of a pressure vessel, high temperature furnace, pressurizing system, controls and auxiliary systems, like auxiliary means the material handling, vacuum pumps, metering pumps, etc. So, this is a typical pressure vessel of the hot isostatic press that is shown over here, where you can see the fluid is there as a pressurizing media, and also the heating coils are there which are responsible for heating the powder aggregate. So, you can see so this is a this is a simultaneous application of pressure and temperature, where you can see that both are talking about a holding stage, that means where the pressure and temperature is kept constant and which is simultaneously exerted over the powder aggregate to achieve the desired part geometry. Okay. So, so hot isostatic pressing, in this case the pressurizing gas which is usually argon is let into the vessel, and then a compressor is used to increase the pressure to the desired level. So, the furnace is then started and both temperature and pressure are increased to a required value. So, this is how a typical hot isostatic pressing setup operates. So, you can get the details of all the functional parts like vacuum pump, compressor and the pressure vessel, which is responsible to keep the pressurizing fluidized body are all shown over here. So, HIP presses are available in diameters up to 2 meter with pressure ranges from 40 to 300 MPa with temperature ranges from 500 to 2200 degrees centigrade. So, one thing is interesting to note here. So, compared to the cold isostatic pressing that we have discussed earlier, so I would like to draw your attention to the the pressure regime. So, like we have mentioned, so here it is not mentioned here. So, in this case the applied pressure is limited to 300 MPa, which is lesser than what we generally exert in case of cold isostatic pressing, which goes beyond 500 MPa. Why is that? Because we are talking about significantly higher temperature, and that can cause damage to the dies, damage to the system if we apply higher pressure. Moreover, in hot isostatic pressing the demand for the applied pressure is lesser compared to what we need in case of cold isostatic pressing to achieve the similar level of density in the sintered parts. So the processing time can last up to 4 hours in case of HIP depending on the material and size of the part. So, during HIP the pores are closed by flow of matter by diffusion and creep, but also bonded across the interface to form a continuous material. So, commonly used heating elements in case of hot isostatic pressing are like Canthal heating element up to 1200 degree centigrade, and in between 1200 to 1700 degree centigrade we generally use molybdenum heating element, and then beyond 1700 degree centigrade it is the graphite which is used as a heating element material for hot isostatic pressing. So, now we have discussed about some of the pressure assisted powder metallurgy techniques. So, we will discuss about some of the techniques which are pressure does not exert that much pressure, however, which are very much beneficial and popular as a PM technique, and also capable of providing parts in net shape. So, not near net shape, that means without any need of any post machining. For example, powder injection molding, we will be discussing about that later, a little later, but before that let us discuss about the powder preparation techniques in detail. So, if you remember, so we have discussed earlier that atomization among other techniques like reduction, like electrolysis, atomization serves as a one of the key technique to develop mostly the metal powders with the desired level of powder size characteristics. So, atomization is nothing but the melting and then atomization of the powder melt film in the form of drops, and then subsequent solidification and cooling of these droplets so that we can achieve the desired dimension of the powder particles. So, there are multiple stages involved in case of atomization. So, in stage 1 we see the growth of waves in liquid sheet, and then in stage 2 we see the fragmentation of and formation of ligaments from the liquid sheet melt sheet, and then in stage 3 we see further breakage of these ligaments of the liquid melt into droplets, which then get solidified in the form of powder particles. So, In most cases, additional processing becomes necessary before the powders attain their desired properties, that is reduction of surface oxides, degashing, size classification, etc., that is needed for the powders which are manufactured via atomization route. So, but however, their manufacturing, so atomization is the primary technique for developing metal powders. Of course, we can develop some irregular size powder particles even by machining route also, that means we can get them from the machine chips of the material, but they are of highly irregular shape, and also we cannot achieve the finer powder particle size that is needed for critical micro components. I mean we generally the thumb rule is the powder particle size should be at least 1/10 of the minimum dimension of the component minimum dimension present in the component. So often so if we need to develop the features in the form of micrometer, so then we need to use the powder in the range of nanometers. So that is also quite common in case of medical field, for medical devices. Even similar research is going on in our group. So then developing these nano size powder particles, often we resort to atomization techniques. So what are the atomization techniques, what are their ranges in terms of the powder particle shape that we can go for, we can achieve, we will learn about it. So so in most cases, like I told, the additional processing steps are needed after production of the powder particles by atomization route. For each of the process stages, different methods can be used, resulting in many variants. So you can so there are so based on the appropriate technique used for melt preparation and disintegration of the melt in the form of powder particles, the atomization techniques can be classified. So this can be by capillary forces like melt drop process, mechanical impact which is called impact disintegration, electrostatic forces, that is electrodynamic atomization, with the help of liquid or gas streams, we call it as water and gas atomization, and then centrifugal forces, we can call it as centrifugal atomization. So you can understand that we are classifying the atomization technique based on the technique of disintegration of the liquid film in the form of droplets, and also we classify the atomization techniques based on the route by which we manufacture the liquid melt also itself for disintegration or rapid solidification in the form of droplets or in the form of powder particles. So so let us go ahead. So in the melting stage, the most important criteria is whether melting and melt distribution requires a crucible system or not. So crucibles are one of the main sources for contamination of atomized powder. So the second criterion is the heating source. So essentially all melting techniques known in metallurgy can be used, such as induction melting or electron beam melting, plasma based melting of the ingot, so that we for melt preparation, but some of these may also contribute to contamination, as for example in arc melting. So so the melting can be done using crucibles, or it can be heating source can be induction, arc, plasma, electron beam, etc. Melt disintegration deals with melt volume, that means melt pool, melt stream, melt film, melt droplet, and also energy input for disintegration to be achieved in the liquid melt stream can be by mechanical means, can be by liquid or gaseous media, by rotational energy, by ultrasonic vibration, etc. So now we will discuss about them individually. So the various melt disintegration methods, number one is the method based on capillary drop formation. So in the melt drop process, the liquid metal flows vertically through the outlet capillary of a tun dish, which controls the melt stream diameter ds. So the melt stream breaks up into droplets of a diameter dd, which depends mainly on ds and only slightly on the melt viscosity nu s and the surface tension gamma s of the liquid melt. So within the usual range of properties of liquid metals, the correlation between ds and dn can be so not d, it should be dd. So there is an error. So this is the droplet diameter. can be approximated by this equation, that is the droplet diameter is approximately 1.88 of the diameter of the melt stream that is coming out from the turn dish. So, this is a typical schematic of the capillary drop formation you can see. So, this is the diameter of the capillary melt stream, and then after dropping over the coming out of the this capillary channel, it is the diameter of the droplet that it is becoming. So, you can understand from here. So, d that is the droplet diameter is greater than the ds, that means diameter of the liquid film or the capillary flow, and then further that this droplet impinges over the metallic base plate, and then it gets disintegrated, and then it generates basically secondary droplets, which are basically then solidified in the form of powder particles, and those diameter of the secondary droplets, which are much lesser in dimension, much lesser in diameter, are marked here as diameter small d. So, now, the resulting particle size is that we can mark is as small d, secondary droplet, or you can also mark it as d2. So, then they are you can express, we can evaluate the size of the secondary droplets dd, or d is equal to small dd, that is the primary droplet diameter nu c Vc by Bp. So, a smaller particle size can be achieved by impact disintegration by the resulting droplets. The relation between the diameter of the secondary and primary droplet is given by this. Vc is the minimum velocity for needed for droplet breakup, and impact velocity Vp to break droplets. So, cooling rates exceeds 107 Kelvin per second enables the production of amorphous powders on a cooled impact surface. So, we can basically achieve amorphous powders also in this case, in case of capillary drop technique. So, and then so in case of electrodynamic atomization, so this process forms droplets using a capillary orifice, applying a DC voltage of 3 to 20 kV between the orifice and a perforated electrode plate. So, that is what is shown over here. So, you can see that this is a typical setup used. So, the capillary channel that is used in case of capillary drop formation or melt disintegration is similar in case of electrodynamic melt atomization also. However, in this case, in spite of a physical impact or mechanical disintegration, it is the electrodynamic, by applying the DC voltage, basically we are trying to achieve this droplets, or having the desired set of diameter and subsequent powder particle preparation. And then fine powder production. So, melt droplets positively charged are emitted from the orifice, creating particle sizes in the range of 0.1 to 10 micrometer, which is finer compared to other atomization process. So, the benefit of this electrodynamic atomization is that we can go for finer particle size of the powders. So, capillary size and particle output, a capillary diameter of 76 micrometer is used, producing extremely fine powder suitable for specialized applications. However, the limitation of electrodynamic melt atomization is that it is suitable for lab scale applications only, because its capacity is limited to grams per hour. So, forget about kgs. So, that is why it is not it cannot cater to the need of several industries which demands for powders and powder subsequent powder metallurgy based processing of those powders by conventional PM route or by additive route. So, hence it demands for resorting to other advanced atomization techniques that we will be discussing in the subsequent classes. So, for this class we are stopping here, and we will meet soon in the next class. Thank you.